Okay, here's 10.5. We're going to get into permutations and combinations. So first I want to look at some password problems, which you can definitely do using permutations. But I like to use the fundamental counting principle. I think that's the easiest way to do these, and I'll show you how this works. So a password consists of 3 digits followed by 2 letters. So first I like to just kind of set up a skeleton of what the password would look like. So these would be the digits, those would be the letters, okay? And I just had a dash to separate them. What I like to do is think about each blank as kind of a category, and using the fundamental counting principle, digits, let's assume we can use 0 as one of the digits. Well, then there are 10 possible things you could put in this first space. You could put 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. And in the second slot, you can also put 10 things in, and same in the third slot. When we get to the letters, well, we've got 26 letters in the English language, so we've got A through Z, right, to choose from, and same thing in that last slot. So now if you think about each of these as a category using the fundamental counting principle, we can just multiply. It's just like when you're rolling dice. If you roll 2 dice, 6 things can happen on the first one, 6 things can happen on the second, assuming it's 6-sided. And then 6 times 6 is 36. So there's 36 things that can happen when you roll 2 number cubes or die. And that means we can use the same kind of principle here, the fundamental counting principle, and multiply this all up. And then we got a whole lot of different passwords that could be made using that format, 676,000 of them. Okay. This is part B. This time, no repeats. No digits or letters are allowed to be repeated. So in the first slot, we still have all 10 digits to choose from, but then let's say our first digit, let's say we put a 7 in there. Well, then we can't use the 7 again, so now we only have 9 digits left, and then we've used a second digit, so on this third slot, we'd only have 8 digits left. Okay? And the same kind of thing happens with the letters. If we use the letter Z first, well, then we've only got 25 letters to choose from on that second slot. And then I multiply all these up. So there's going to be less passwords available if you can't have repeats, but still a whole lot. It's still 468,000 combinations there. Okay, or I should really say permutations. Okay, next up we're going to evaluate this. 5. It's actually 5. It looks like an exclamation mark. It's the same symbol, but in probability and in math, this means 5 factorial. So this symbol means factorial. And here is what it means. This means it's 5 times 4 times 3 times 2 times 1. So it's all of the you use all of the integers going down to 1 and multiply them all together. It's the product of all the integers going down from there. So when you multiply this all together, that's going to be 120. Okay. And I'm going to do the problems on the rest of this with calculator mostly, but if you want to do them without calculator, it's really, without a calculator, you really have to understand what factorial is. Okay? All right, so let's look at a permutation first. So a permutation is an arrangement of things where order matters. And that'll be easier for me to explain when we get into some examples. But first, let me just talk about the formula. So here it is. So we've got the P for a permutation to show that this is a permutation. Okay. We also have combinations, which I just have a C here instead. The formula is different, but this is P for permutation. Okay. And N is the amount of objects, and R is how many of them you're choosing at a time. So you know, when we were talking about choosing letters out of the alphabet, let's say we had to make a five-letter word. Well, then we'd have 26 as our N, and we'd have 5 as our R. We're choosing 5 letters out of the alphabet, out of a total of 26. Okay? And the formula looks like this: n factorial over n minus r factorial. Okay? So on a graphing calculator, here are the steps, and I'll show you that with this example. But let's set this up without a calculator first. So I would put in 5 is going to be my n, right? So that goes up there. So we have five objects taken 2 at a time. All right, and on the bottom, n minus r, so that's going to be 5 minus 2, and then factorial again. Okay, so on top this means 5 times 4 times 3 times 2 times 1. On bottom this would be 3 factorial, which is 3 times 2 times 1. So actually this one is pretty easy to do without a calculator because, hey, the 3's, the 2's, and the 1's are all going to reduce. They're all going to cancel, and then I'm just left with 20. Okay. When we have larger numbers, these numbers get big really quickly, and it gets harder to do that by hand. But you could always do these by hand like this. But let's look. I'm going to use a TI 84, but it'll be the same really on most TI calculators, TI graphing calculators at least. So what I want to do first is go to the math menu. Okay. So I've got this math button right here. It's a third button down on the left or fourth button down, depending on where you're counting. Okay, and then we want to go over to probability. That's at the top, and it actually the older calculators it looks like this, but this is a newer one and it has PROB. But I want to go to the column. I just scrolled over the column that says probability, and then the second choice there is NPR. That's for a permutation. Right below that, this is what we're going to use for a combination. You can see there's factorial. If you want to find 27 factorial, you could do it that way as well, instead of typing out 27 times 26 and so forth. Okay, but here we're using this one, okay? And I've got these two little places where I can plug in the 5 and the 2. On some calculators, you might have to type 5 first, then go, so that's why I have the N first. On some calculators, you're going to have to put 5 first, then all this stuff, then the 2. Other calculators, if it has the cursor just in those 2 slots, you can just type it in like that. Okay. All right, so 8 equals 20, right? Same kind of deal. So yeah, on that example, this would be the 5 and the 2. So it depends if it will put the cursor there for you or not. Okay. Okay, so there's the formula for a permutation. Let's look at the formula for a combination. It makes better sense to have those formulas under our belt before we start really looking at some examples. So a combination is an arrangement of things where the order doesn't matter. Okay, so the order does not matter, and I'll explain that later, but the formula is a little bit different for a combination. You see we've got this added component here, okay? So, same kind of thing on a graphing calculator. So actually I should do it without a calculator first. 5 factorial would go there, right? And I'd have 5 minus 2 here. But then I also I'm multiplying by r factorial, so by 2 factorial. So if we think about what we got here, on top, 5 times 4 times 3 times 2 times 1. And then I've got 3 factorial, which would be 3 times 2 times 1. And I've got 2 factorial, which is 2 times 1. Okay, so we can still do quite a bit of canceling here. And then, let's see, I've got 20 over 2, which is going to be 10. Okay, so I really don't need a calculator there. It's not too bad to do by hand. But let's look at how to do it with a calculator. And it's the same kind of deal. I'm just going to choose the combination instead of the permutation function when I get to that menu. Okay, so I'm going to hit the math button. I'm going to go over to the probability column, and I'm choosing NCR. And again, you might have to type in the 5 first, and then the 2 at the end. Mine has those cursors there, so I just type them in like that, and that gives me the same result. Okay. All right, so now let's look at some actual examples. So let's say 2 students out of 35 are randomly picked to take out the recycling. Let's say for my class, I'm going to have 2 people take out the recycling. Does the order matter? So let's say I choose Joe and Sally. Well, is choosing Joe and Sally to take out the recycling the same as choosing Sally and Joe? Say I'm choosing them one at a time. Well, that's the same, right? It doesn't matter because the 2 people are doing the same job. So it doesn't matter what order you call the people's name out. So that order does not matter, and that tells me that this is going to be a combination. Okay, I'm going to use a combination. So then when I'm figuring out how many possible groups there are that could take out the recycling, if I'm randomly drawing their names out of a hat, now I know I've got 35 total students. It's a combination. 2 of them are getting picked. So this would take a while to do with the formula. I'm going to use a calculator. So I'm hitting math, probability. I'll choose the combination, and I'm going to hit in 35. Oops. Let me go back there. I hit enter too soon. So I hit 35 and scroll over and put the 2 in. If you put 2 in the first slot and 35 in the second slot on accident, you'll get an error. But this gives me 595. Okay, so 595 groups. Okay, let's look at a similar example. This time we're going to randomly pick someone from the class to be president and to be vice president. So you need to think, does order matter here? Let's say the first person you choose is the president, and the second person you randomly choose is the vice president. Well, if you switch the president and vice president, right? If Biden's president and Harris is vice president, if you switch that, then that does matter, right? That's a different combination, a different group. That's a whole different thing. So the order does matter because these jobs are different, right? We've got president and vice president, and those are totally different jobs. So if you switch the order, it does matter. So that means that this is going to be a permutation, and then we'll do 35. 2 are getting picked, but switching the order of those 2 people gives you a new group. So hit 35. Oh no, I'm not hitting 35 first. Math, probability. I'll choose the NPR one this time. 35. 2, and so we got 1190. Okay, so we got more because you can get a second group out of the same 2 people if you switch their roles, right? So that we really got twice as many groups for that reason. Okay, let's try a couple more examples. So it's really important on these that you understand the difference between a permutation and a combination. So it all has to do with, does the order matter or not? So I've got some more examples to try to illustrate that here. So here we have a raffle with 100 tickets sold. There's going to be 3 winning tickets. Okay, and it says each winner receives a fabulous diamond ring. So let's say Larry, Curly, and Mo are the winners. They all win diamond rings. Does it matter which order their names get called? Well, they're all getting the same prize, right? So here the order does not matter. That means we've got a combination, not a permutation. Okay, so we have 100 people. 3 are getting chosen, and the order does not matter. So I'm going to hit math, go over to probability, and I'm going to choose the combination function then. And I'll put in my 100 and my 3, and that's going to give me 161,700 possible winning groups. Okay, so that would be the odds of those 3 people, the probability of those 3 people getting selected. Okay. All right. Now we got another raffle. Same kind of deal. We got 100 tickets getting sold. 3 are randomly drawn. It says the person holding the first ticket drawn wins a castle built of gold. Yes, nice. The holder of the second ticket wins a fantastic new car. Not bad. Holder of the third ticket wins a wonderful mug. Well, that's nice too, right? But this is a big difference between these different prizes. So that means it definitely matters, right? If you're wanting the winners, you probably would prefer one of the other prizes as opposed to the mug, right? So the order really matters. Larry, Curly, and Mo getting drawn out is not the same as Mo, Curly, and Larry. So the order does matter here. That means that this is going to be a permutation. Okay, and so when we type that in, we got 100. 3 of them are getting picked, but it's a permutation. Whoops, I like to do that because my old calculator, I have to do that, but hit the math key first, and then put it in like so. And since you can switch around Larry, Curly, and Mo in a couple of different ways, that means you're going to get more groups, more more combinations, right? That is the end of the section, and I'll see you next time.